In the last several videos, we've considered how a single substituent affects electrophilic aromatic substitution. In this video, we're going to think about what factors need to be taken into account when we have multiple substituents. So it's important to consider the directional effects of all the substituents attached to a ring when we're doing electrophilic aromatic substitution. In this first example, things are pretty easy. We have a methyl group, which is an ortho-para director, and we have an NO2 group, which is a meta-director. So the ortho-para director is going to want to put things in the para position, but there's already something there, so it can't put things there, or it wants to put things in the para position. Well, the para position to the methyl group is also the meta position of the nitro group. So in this case, we only get a single product. We just get the bromine added to this position. That's ortho to the ortho director, and that's meta to the meta director. So the more interesting examples occur when substituents attached to the benzene ring will direct the group that we're adding to different positions. In this case, we have an OH group, which is an ortho-para director, and a methyl group, which is an ortho-para director. And so both groups would like to put things in the para position, but for both groups, that's blocked. So the OH would like to put the NO2 group here or here. The methyl would like to put it here or here. So the way we resolve this conflict is we have to determine which group is the strongest activator. Because OH is a strong activator and methyl is a weak activator, the directing effects of the OH are going to dominate where the NO2 group is going to add. And so because the OH group is the stronger activating group, it's going to control where the NO2 goes. And so it's going to add para to the stronger activator. All right, so let's look at an example. We want to predict the products of the following reaction. So these reactants are going to add a bromine to our starting compound. And so we need to consider the activating effects of each of our groups. This first group here is going to be electron withdrawing. So it's going to be moderately deactivating. We have a methyl group, which is a weak activator. And then we have this group, which can contribute electron density by resonance, but it also will contribute electron density in this direction outside of the ring by resonance. So it's going to be a moderate activator. But among the three groups that we have, this is the one that's the most strongly activating. So it's going to determine where the bromine is going to add. So it's an ortho-para director because it's activating, but the para position is taken. This ortho position is taken, so the bromine can only add here. So my products are going to be, or my product, as this case is, so my bromine will add to that position. All right, so the two big things that we have to consider when we have multiple substituents is we have to determine which substituent on the benzene ring is the strongest activator. It will determine the directing effects, but we also have to consider the effects of steric hindrance. Now, the book gives a couple of rules, and so I follow the same thing in my video here, but I don't really consider each of these individual rules. I just consider, sort of what we know about steric hindrance overall, right? Big things get in the way, and so groups want to spread out so that they're not bumping into each other. That's really the heart of steric hindrance. So we already kind of talked about this first rule in previous videos, but generally if I have an ortho-para director, the para product is favored over the ortho product due to sterics. Right, I've got this big isopropyl group, and so it's tough for the NO2 to get in here and add in the ortho position, and so adding in the para position is going to be the major product. I think the one exception we saw to this is when we had a methyl group, where in that case the ortho was actually the major product. But the vast majority of the time when we have ortho-para directors, if it's just a single substituent, it's going to add in the para position. All right, now in the case of 1,4 disubstituted rings, substitution will generally occur at the less sterically hindered site if more than one site is favored by directing effects. So in this case, I have two weakly activating groups, and they're both ortho-para directors, and so the isopropyl group is going to try to direct the NO2 to one of these positions. The methyl group is going to try to direct it to one of these two positions. But because the isopropyl group is bigger, there's more steric hindrance at these two sites, and so the NO2 is going to preferentially add to the less sterically hindered site. And so this is going to be our major product, and when it adds next to the isopropyl is going to be our minor product. Okay, here's an example with a 1,3 disubstituted ring, and sort of the point of this rule is that this site is particularly unfavorable from a steric perspective. So if we just consider the directing effects, these are both weakly activating, they're both ortho-para directors, and so the most likely sites from a directing or an electronic perspective would be here, here, or here. And sort of break that tie, we'll look at the sterics. Right, this is the least favorable position, and in fact that product is not observed. And then comparing these two, this is the less sterically hindered site, so that's going to be our major product, and then the more sterically hindered site is going to be the minor product. Okay, so here are two examples. For each compound, I want to determine which position is the most likely to have a substituent added through an electrophilic aromatic substitution reaction. So in this first compound, I have to decide which substituent is going to determine the directing effects. The halogen is weakly deactivating, the ethyl group is weakly activating, but this methoxy group is going to be sort of on the strong end of the moderate directors, or as I said, some textbooks even just classify this as a strongly activating group. So this is going to determine the directing effects. It's an ortho-para director, so the para position is taken, so it's going to want to add the groups to one of the ortho positions. But this position is more sterically hindered due to its proximity to this ethyl group, and so this is the site where we're going to add, where we'd add a group through EAS. All right, in this compound, I have two moderately activating groups, right? They can contribute electron density to the benzene ring through these lone pairs that they have. But we're also going to lose some of that electron density to the resonance that it's going to participate in that's outside of the benzene ring. So I have two moderate activators. They're both ortho-para directors. In each case, the para position is taken. So this group is going to want to add it to one of these ortho positions. This group is going to add it to one of these ortho positions. But this is the bulkier group, so these two sites are going to be more sterically hindered. So the positions where I'm going to add through EAS are going to be one of these two positions. And of course, they would be identical due to the symmetry of the molecule. Okay, so the last thing I want to consider in this video is the idea of blocking groups. As a sort of introduction to this, let's say I started with this compound and I wanted to add a bromine to the ortho position. Well, this tert-butyl group is very bulky, and so sterically, the bromine is going to prefer to add to the para position. So this is where the idea of blocking groups come in. I could use a blocking group to prevent substitution at the para position. So if I was to first add a group at the para position, I could then brominate it where it's going to add to one of the ortho positions because the para position was taken, and then I need some reaction to take that blocking group back off. Back in one of the early videos for this chapter where we mentioned that sulfonation was reversible and that it would become important later on. Well, this is the point later on where the reversibility of the sulfonation reaction becomes important. The fact that the addition of the SO3H group is reversible makes it a good choice for a blocking group. I can add the SO3H using concentrated fuming sulfuric acid, and I can take off that SO3H group by adding dilute sulfuric acid. So To more specifically accomplish the synthesis that was presented on the last slide, right, we would first react this compound with fuming sulfuric acid. That will preferentially add the SO3H to the pair position. I can then use bromination to add the bromine to one of the ortho positions, then hit it with dilute sulfuric acid to take that SO3H group back off and yield the product that I was interested in. Okay, here's one last example. So I want to synthesize this compound from this starting material. Now, if I just try to hit this with the nitration reaction, this is a strong activator. This is a weak activator, so this will determine the directing effects. So this ortho position is taken. We could add to this ortho position or this pair position. But we know that due to steric hindrance, we're more likely to add it to the pair position. So in this case, we're going to have to use a blocking group. So I can use sulfonation to put on a blocking group, then use nitration. And so the only now open position for the NO2 group to go is here. And then I can take that blocking group back off. So to add the blocking group, I'll use fuming concentrated sulfuric acid. Now I can do the nitration using a mixture of nitric acid and sulfuric acid. And I can take that blocking group back off by using dilute sulfuric acid.